one we had last time. That is, on the right-hand side, we have something that depends on the chemical potential. While the equation of state is always in the form P times V equal to 1 over beta times some function of n and possibly other variables. But it's certainly not a function of the chemical potential. Therefore, we should figure out an equation for the number of particles as a function of chemical potential, solve this equation for the chemical potential, substitute here, and figure out what is the equation of state. Now, of course, the equation for the number of particles as a function of chemical potential is given by the obvious equation, which is sum over P, 1 over e to the beta epsilon P minus mu plus 1. The plus 1 because we're dealing with fermions. Okay, so now in principle, the way you proceed is by taking these two equations. You solve mu as a function of n in the second equation, then you substitute in the first and you have the equation of state. Now, this is easier to say than to do. In practice, life is a bit more complicated because you have to compute these sums, and these sums are not easy to compute in general. So let's do it in 3 dimensions. So let's focus on d equal 3 now. And let me show you how to do this calculation in 3 dimensions. Now, in 3 dimensions, you have P times V divided by K Boltzmann T equal to, so let's take, I have sum over P. I can transform this sum into an integral. So I will have V over H cubed. H is the Planck constant. Integral dp, or actually I can forget about H. Let me write it as, let me set H bar equal 1 and 2 pi cube dp. So I will have a 3-dimensional integral log of 1 plus e to the minus beta epsilon p minus mu. So now let me assume that these fermions are sitting in free space. And in practice, fermions are never sitting in free space. They are sitting in a solid with a certain dispersion, which depends on the band structure and whatever. Or they are sitting in a trap for cold atoms. But it doesn't matter. Let me just, for simplicity, think of these free fermions in free space, in which case epsilon p is just p squared over 2m. So it depends on the absolute value of p. It's essentially spherically symmetric. Let me write it explicitly. So if it's spherically symmetric, then this integral can be performed in spherical coordinates. So I will have v over 2 pi cube times the solid angle, which is 4 pi, and then the integral between 0 and plus infinity, dp, p squared, and then the log of 1 plus e to the minus beta p squared over 2m minus mu. Okay? So this e to the beta, this object here, I can rewrite it as z, the fugacity, times e to the minus beta p squared over 2m. right? Because the fugacity is e to the beta mu.
Professor,
Yes.
I'm trying to see how you got 4 pi. I do not see it clearly.
Well, so I have an integral dp, right, of some function of the absolute value of p. So I do this integral in spherical coordinates. So I have the integral between 0 and pi d theta of, wait a second, it's r squared cos theta, right? In the volume element.
It's sine theta.
Just a second.
It's sine theta d
Sine
theta
theta, right?
d phi.
2 pi d phi, and then
Sine theta.
yes, it's sine theta, r squared, sorry, p squared sine theta of f of p,
A.
right? And now I can do the integral over d theta, and I get 2. I do the integral over d phi, and I get 2 pi. And therefore this is equal, and then there is an integral dp, 0 plus infinity. So this is integral 0 plus infinity dp p squared times 4 pi times f of p. Okay? Is it okay now?
Yes, it's okay.
Okay. So I can erase this.
Professor,
Yes.
actually, I'm a little bit confused on how you approach the PV as I mean the PV equation as an integral before you have sum of P, right? So yeah, so how do you approach it as an integral? What assumptions you make or something?
I'm assuming that, so, okay, you're asking me what assumptions, what allows me to transform the sum into an integral. So because here I have sum over p of some function of p, right? For some function actually of epsilon p, right?
Yes.
And now I'm transforming this into an integral v over 2 pi cube integral dp of the same function. Well, so what I want is that this function is a smooth function of epsilon p. What does it mean to be a smooth function? So let me calculate. So the p is quantized in units 2 pi n over L, right? I mean, each component, right? So let me think about one component changing by, in which n changes by units. So let me take p prime equal to 2 pi n plus 1 over L, and then p equal to 2 pi n over L. And now let me compute the epsilon p prime. So epsilon p prime is p squared, p prime squared over 2m. And this is equal to, so is equal to p plus 2 pi over L squared over 2m. So in other words, is p squared over 2m plus 2 pi over L, actually 4 pi over L, p over 2m plus etc., etc. So this goes with that. Have a factor of 2. Okay. So now you see that this is equal to epsilon of p plus 2 pi over L times p over m. So in other words, is epsilon p plus delta p times the velocity, because p over m is the velocity. This is p over m. All right, so now what I want is that essentially this function is seen as a smooth function, as a continuous function of its argument, this one, in such a way that I can essentially transform this sum into an integral. And you see that this is true as long as kBt is much larger, or is larger than delta p over v times v, right? Or in other words, then 2 pi over L times v. And in particular, this is true in the thermodynamic limit when you set L to infinity. So when the system size is large. When the system size is large, you're putting periodic boundary conditions, but the gap that you have among subsequent levels is very, very tiny on a scale of temperature. So in practice, the function is a smooth function, and I can estimate the sum as an integral. You see what I mean?
Sorry, can you repeat the last sentence?
When the system is in the thermodynamic limit, as you see from this argument, so if you send L to infinity, then the gap in the spectrum of your free particle system, essentially, the gap among subsequent levels is always much, much smaller than any other relevant energy scale, in particular the kBt. And therefore, the function f is a smooth function of its arguments, and I can estimate the sum of f of epsilon p as an integral. Okay?
Yes,
So
yes.
that's essentially the logic. So in the thermodynamic, so therefore the short answer to your question is in the thermodynamic limit, when L goes to infinity. Clear page. All right, so, okay, so this is the first equation. And then of course I have a second equation for n, which is n equal to v over 2 pi cubed times the integral dp, and then I will have 4 pi p squared 1 over e z e to the beta p squared over 2m plus 1. So these are the two equations. Now, in order to sort out what is n, what is the fugacity z as a function of n, I have to compute these integrals. So let me do it for the first, and then essentially for the second is the same story. For the first, let me first of all change variables. So let me rewrite this stuff in the next page. No. let me take it to the next page. Okay. So this is equal to V over 2 pi cube and then you have 4 pi integral between 0 and plus infinity dp p squared log of 1 plus z e to the minus beta over 2m p squared. So now let me do the following. Let me set beta over 2m p squared equal to x squared. So let me change variables in the integration. If I do so, then what I will get here is v over 2 pi, is the following, is, well, since I have a v on both sides, let me just eliminate it. So p over kdt equal to 1 over lambda cube f of z, where lambda is equal to the square root of 1 over 2 pi m kbt, and f of z is equal to 4 over square root of pi integral between 0 and plus infinity dx x squared log of 1 plus e to the minus x squared times zeta. What I wrote here is the result of a change of variables, nothing else. By the way, you can do the similar change of variables for the second integral. I'm not going to go through the calculation because it's analogous to the first, but I will write down in a second the final result. All right, so now we are facing the problem of computing this complicated integral for f of z. How do we do that? Well, so let me take it to the next page and show you how to do this integration. What I can do is expand in a power series of z this log, right? So I will obtain that this is equal to 4 over square root of pi integral between 0 and plus infinity dx, and then x squared z e to the minus x squared minus z squared over 2 e to the minus 2x squared plus z cubed over 3 e to the minus 3x squared plus etc. minus and whatever. And then you go on. This is the expansion of log of 1 plus z, right? You know that log of 1 plus x is equal to x minus x over 2 plus x over 3 minus x over 4, blah, 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 blah. Okay?
You forgot the power.
Squared and cube. All right? So now, let us take this and calculate each one of these integrals. Well, you see here I have x squared, here I have e to the minus 2x squared, here I have e to the minus 3x squared. Now, if in this integral I make a change of variables and I set 2x squared equal to x prime squared, and in this one I set 3x squared equal to x prime squared, what I will get is the following expression, is 4 over square root of pi, integral between 0 and plus infinity dx of x squared z e to the minus x squared minus z squared, and then I will have 2 times just a second, 2 to the power 3 halves e to the minus x squared plus z cubed divided by 3 times 3 to the power 5 halves, no, 3 halves, not 5 halves, e to the minus x squared minus etc., etc., etc. Now I can collect all the terms that contain e to the minus x, and I obtain 4 over square root of pi integral between 0 and plus infinity dx of x squared e to the minus x squared, and then I have z minus z squared over 2 to the 5 halves plus z cubed over 3 to the 5 halves minus etc., etc., etc. This integral here, I know how to compute it. It gives me essentially square root of pi over 4. So overall, this stuff is normalized to 1, and therefore what I get is that this is equal to the sum for L from 1 to plus infinity. Here I'm extrapolating the result of the summation of these first three terms to all of them. It's straightforward to see that it's correct. Z to the power L minus 1 to the power L plus 1 divided by L to the power 5 halves. So that's why I'll call this function f of 5 halves z. Now, it turns out that, so this allows me to essentially sort out what is the first of these two equations. Now, the second equation is actually as simple as the first. So I will have P over KBT equal to sum over L from 1 to plus infinity minus 1 to the power L plus 1 Z to the L divided by L to the 5 halves lambda cube. So this is the first equation. And the second equation is n over v equal to sum over L from 1 to plus infinity of minus 1 L plus 1 z to the L, and then I will have L to the power 3/2 lambda cube. So these are the two equations that allow you to reconstruct order by order in this expansion in Z the equation of state.
Professor,
Yes,
I have a question on the previous page.
yes.
Mm, mm, you said why you look at the third line from down. Why
So
did you the third
the
line
third
from
one,
down? Yes.
yes.
Why did you have to put the 2 dot those 2 3/2? Or
Well, because I'm changing variable, right? So I'm setting 2x equal to x prime, right? So now you see that I have here x cubed. So what this means is that x prime is equal to square root of 2 times x. So this is what this change of variables means. And therefore, dx x squared is dx prime x prime squared divided by 2 to the 3/2 for this term here. And for the other one is going to be 3 to the 3/2 and so on and so far. You see, it comes from this.
okay, thank you.
All right. So you see these two equations essentially allow you order by order in perturbation theory, I mean in this expansion, to find Z as a function of the density, right? And then you substitute and you find your equation of state for the fermions. Now this is a process that is not problematic at all because Z can have any value for the, I mean, is a positive number, of course, but can have any value for an expansion of this type. It could be greater than 1, in which case the chemical potential is positive, or it could be smaller than 1, in which case the chemical potential is negative. I mean, there's no problem for fermions, right? There's absolutely no problem for fermions. You don't have anything that is constraining the value of the chemical potential. For bosons, as I told you, it's a completely different story. Because for bosons, the chemical potential has to be necessary. If I have a dispersion p squared over 2m, then the chemical potential has to be necessarily negative. Okay? So let us do the analog calculation, like this one, for bosons. Focus on bosons.
Is that now?
What?
Focus what on bosons?
What?
Sorry. I'm trying to read what you just wrote.
Focus now on bosons.
Oh, okay.
Okay. So, Bosons. The difference between fermions and bosons is that for bosons, the distribution function, as we all know, is the Bose-Einstein distribution, right? Which is 1 over e to the beta epsilon p minus mu minus 1. And as we said, mu has to be smaller or equal to 0. Okay? Now, how do you find the chemical potential? Well, you fix the number of particles. The number of particles is given, and then for each temperature, you solve the following equation. Sum over P, 1 over e to the beta epsilon p minus mu minus 1 equal to n. Now notice that in principle, for any system, this equation contains a sum, right? So when I have a sum of this type, I'm summing over the ground state, e to the beta epsilon, ground state epsilon naught minus mu minus 1, and then the excited states, e to the beta epsilon p minus mu, epsilon p1 minus mu minus 1, plus, etc., etc. Okay? In general, for any system having a finite size, this is a discrete sum. This we know very well. So in practice, this sum will contain the contribution of the ground state, and this one will obtain a contribution for excited states. So all of these guys are going to be the contribution that come from the fact that I can occupy also excited states with bosons, not only the ground state. Now, all of this distinction that is always present in a sum will disappear the moment we take the thermodynamic limit. We imagine sending L to infinity, or L much, much larger than whatever. And therefore, we approximate this as V over 2 pi cube. Let's say we are in 3 dimensions, integral dp 1 over e to the beta epsilon p minus mu minus 1, right? Which in practice is, as we all know, equal to, I can always do the integral in spherical coordinates. I will get a 4 pi squared, and therefore this is going to be V over 2 pi squared integral dp 0 plus infinity dp p squared 1 over e to the beta epsilon p minus mu minus 1. Okay? Now, I can further simplify this integral considering the fact that if epsilon p is p squared over 2m, then I can change variables, set this combination equal to epsilon, then d epsilon is equal to p over m dp, or writing it in terms of epsilon, square root of 2 epsilon over m d epsilon Making this change of variables gets you a function of epsilon in this integral that is known as the density of states. Did you know this? Have you ever seen this kind of changes of variables?
Yeah.
Good. All right, so let me change variables and pass to the energy representation here. So this is going to be equal to V over 2 pi squared integral between 0 and plus infinity d epsilon of square root of m over 2 epsilon, and then I will have 2m 2m epsilon divided by e to the beta epsilon minus mu minus 1. The 2m epsilon is just p squared. You see that in this integral I have this p squared sitting here. So let me simplify things here. This is equal to v over 2 pi squared. And then I have m to the power 3/2. I have a square root of 2, and then integral between 0 and plus infinity d epsilon square root of epsilon times 1 over e to the beta epsilon minus mu minus 1. Okay? Now, this I can write it as integral between 0 and plus infinity d epsilon g of epsilon. This is the density of states with all the dimensionful constants, etc., etc. 1 over beta epsilon minus mu minus 1, where g of epsilon is just a second. Yeah, is v over square root of 2 pi squared times m to the 3/2 times square root of epsilon. So this thing here is just a constant. What is important is that this function goes like square root of epsilon, close to epsilon equal to 0. Okay? Now, why this is important? Because now, so now you have this equation. Let me rewrite it here. N equal to integral between 0 and plus infinity d epsilon g of epsilon 1 over e to the beta epsilon minus mu minus 1. Now, when the temperature is very large, you can try to figure out what are the solutions to this equation, for example, numerically. Setting a g of epsilon equal to a constant times square root of epsilon, the constant take it dimensionless. And what you will find is that there is a solution that is negative, and it's going to do the following. So for very, very large temperatures, you will find a solution for the chemical potential, which is a negative number. And then this solution keeps growing and growing and growing as you decrease the temperature, going towards 0. So it grows, it grows, it grows. Now, the question I might have is this function ever going to touch 0 at some temperature, or is going to do something like this? It's going to grow, 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 but be always negative. In other words, is there a temperature T, C, such that mu at Tc solution to this equation is equal to 0 or not?
I think yes.
Well, yes, there is, of course.
The requirement is like that from the beginning.
Well, so for this particular case, there is such a solution. But mind something important. It's not always true that, so for a three-dimensional system, we will see in a second that for three-dimensional bosons, there is a temperature such that the chemical potential at that temperature is equal to 0. But for example, for bosons in 2 dimensions, the chemical potential is always negative. So there isn't temperature for which the chemical potential is equal to 0 in that case. So it's not always guaranteed. And my question is not just a rhetorical question. It's a question that has also some substance in it. Anyway, how do I find whether there is a temperature for which the chemical potential is equal to 0? Well, let me set the chemical potential equal to 0, and let me find the temperature T for which n is equal to the integral between 0 and plus infinity in the epsilon of g of epsilon 1 over e to the beta epsilon minus 1, right? It's not difficult to estimate this integral. This is equal to, if I set beta epsilon equal to x, and I change variables, this is c, the constant that was in front of my density of states, over beta to the power 3/2 times the integral between 0 and plus infinity in dx of square root of x e to the x minus 1. This integral is can be found in any book of statistical mechanics or in those books of integrals like Abramovitz Stegun. And what you will get is zeta to the 3/2 gamma to the 3/2. Okay? So this is the result of this integration. And in practice, if this is the result, well, beta we know that is 1 over kBt, and therefore we know that the chemical potential is going to be equal to 0 at a temperature Tc equal to n to the 2/3 time divided by c times gamma to the 3/2 times zeta to the 3/2. Zeta is the Riemann zeta function, 2/3. Okay? So at this temperature, the chemical potential is equal to 0. Okay, so I have something like this with a chemical potential that goes through 0 at this temperature. So the scenario you have is this one, is not the one of a chemical potential that is always negative, like in this curve that I'm erasing now. Good. Now, what happens for temperature smaller than Tc? Well, for temperature smaller than Tc, the problem is that in order to solve this equation, this one, in order to solve this equation, you would need for T smaller than Tc, in order to solve this equation, you would need mu positive. But mu cannot be positive, right? Because otherwise the distribution function of the number of particles is always, it would be meaningless for energies between 0 and mu. And therefore, for all
I'm sorry,
temperatures,
Professor.
yes.
I don't see why you should be positive. Mu, sorry.
Well, because of, just imagine, because of continuity, right? I mean, if you impose this equation, you can put it on a computer if you want, but you can imagine that this curve will start cutting through. In other words, let me put it in a different way. Certainly, you cannot find a solution. Let me put it in a different way, maybe you understand better. For temperature smaller, than Tc, then if you call Nx equal to integral between 0 and plus infinity d epsilon 1 over e to the beta epsilon minus 1 times g of epsilon. This integral here is always smaller than n. Okay? Is always smaller than n. Actually, it tends to 0 when
Professor?
t. Yes?
What is nx?
Well, I'm defining it. This is equal to this integral. Okay? And I'm saying for temperature equal to Tc, this is equal to x. So for T equal to Tc, n Ex is equal to n by definition. But for temperature smaller than Tc, this is smaller than n. And therefore, I cannot satisfy this equation with a chemical potential that is equal to 0, right? But the chemical potential cannot be positive. I cannot cut through this line and make the chemical potential become positive. It would be meaningless physically. So what is going on here? What is going on is the following. You always have to remember that where this integral comes from. This integral comes from this sum. And I told you that this sum has two contributions. One contribution is from occupying with bosons the excited states. So let's call this contribution NEX. And NEX, if you go through the calculation we've done, is going to be equal to integral 0 plus infinity d epsilon g of epsilon 1 e to the beta epsilon minus 1. And then there is a second contribution that is N naught, the occupation of the ground state. Now, what is going on here below Tc, above Tc, for t greater than Tc, NEX with chemical potential mu negative essentially saturates the number of particles. So in practice, all the number of particles are sitting in excited states. An irrelevant number of particles is sitting in the ground state, and it's not important to think about it. If the temperature T is that is smaller than Tc, what happens is that a number of particles equal to NEX, written up here, this one, is occupying excited states. Okay? So this is the number of particles that are sitting in excited states. Excited states. And the number of particles equal to N minus NEX, you see, this is smaller than N. Therefore, a number of particles equal to N minus NEX let's call it N naught, is occupying the ground state. Okay?
What's that last? N minus NX. N naught is what? Like 0?
N naught.
Hmm.
So N naught is the difference between the number of particles in the excited states and the total number of particles. And if you go back to the sum, right, you see that N naught is the occupation of the ground state. But what is so special about this N naught for temperatures smaller than Tc? What is special is that, you see, just a second. What is special is that NEX is an extensive quantity, scales like V. N is an extensive quantity, scales also like V. And naught, well, is also extensive, scales like the volume. Is the difference of two extensive quantities. And if you go through the details, you will see that scales like the volume. So what you have in this situation is a situation in which an extensive number of macroscopic, extensive number of particles are occupying the ground state of your system. Okay? So for temperature below this critical temperature, the chemical potential sticks to 0, and the excess occupation, the one that is not accounted for by excited states, is all going to the ground state. All the particles start occupying macroscopically the ground state. This phenomenon of a macroscopic occupation of the ground state below a certain critical temperature is known in the literature as Bose-Einstein condensation.
Professor.
Yes.
So actually, I'm still a bit confused. So you're saying that above TC, there is only excited states. I mean, the particle only occupies
the ground state is not occupied macroscopically below TC. Well, there are some particles in the ground state, but it's not a macroscopic occupation.
What do you mean by macroscopic occupation?
A number of particles that scales like the volume.
So
look,
okay.
So let me show you the difference. For T greater than Tc, what is the number of particles that occupies something with momentum P? Well, it is 1 over e to the beta epsilon P minus mu minus 1, right? And this is true also for P equals 0, which is the ground state. All right?
Yes.
Now, you see that this is just a number. It's not something that scales like the number of with the volume. So this is what I mean. For T greater than Tc, all states are occupied in a standard way by a finite number of particles. For T smaller than Tc, n of P for P greater than 0 is equal to 1 over e to the beta epsilon P minus 1. Okay? So for all P greater than 0, n for P equals 0 for the ground state is instead equal to n, the total number of particles, minus the integral between 0 and plus infinity d of epsilon g of epsilon over e to the beta epsilon minus 1. But g of epsilon is a constant that is proportional to the volume, right, times square root of epsilon. Therefore, this can be written as n minus integral between 0 and plus infinity d epsilon, this constant, c, square root of epsilon divided by e to the beta epsilon minus 1. And now let me collect the volume. So this is volume times the density minus integral between 0 and plus infinity d epsilon c over the volume, which is another constant c that is not dependent on the volume anymore, minus 1. So you see, while for all momenta greater than 0, the occupation is just a number, for the ground state, P equals 0, the occupation is actually a number, something that scales with the volume. If you increase the volume, you increase the occupation of the ground state. What does it mean? It means that your ground state is actually occupied by a macroscopic number of particles. Macroscopic means that it's something that has a finite density. So is a number of particles that is proportional to the volume of your system. Is it clear now? Hello? Are you still there?
Yeah. So I think I get the point where it's proportional to volume.
Yeah, but what is worrying you?
Maybe I just don't understand some terms that you use. Yeah.
So which ones?
Maybe later along the way.
Okay. Are there other questions, or everybody else understood quickly Bose-Einstein condensation? No more questions? Okay, so if there are no questions, then let me move on. Let me discuss the following thing. I told you, so you might be under the impression that Bose-Einstein condensation is something that happens always, okay? For all systems. So if I take bosons and I put them somewhere, at some point I reduce the temperature and I will get Bose-Einstein condensation. This is not the case, okay? It's actually one of the phenomena in physics that is which the difference in time between the prediction and the observation was the longest. I mean, Bose-Einstein condensation was predicted at the beginning of quantum mechanics, roughly. But then it was properly observed only at the end of last century with cold atoms, essentially in traps. Now, Bose-Einstein condensation is also a phenomenon that needs some peculiar conditions to be satisfied to be observed. In order to see this, let me consider a system with a quadratic dispersion in two spatial dimensions. And let me try to repeat the argument of the previous calculation for this case. So we're sitting in 2 dimensions. I will have sum over P 1 over, so I'm trying to find again the temperature at which the chemical potential is equal to 0 for this system. For this case in 2 dimensions. So if I pass from the sum to the integral, it will have A over 2 pi squared, and then integral dp 1 over e to the beta p squared over 2m minus 1. Then I pass to circle coordinates. So I will have A over 2 pi integral between 0 and plus infinity dp p over e to the beta p squared over 2m minus 1. And now what I do is I set p squared over 2m times beta equal to x, in which case what I have is that this is equal to A over 2 pi. A is the area, of course, of my system, right? It's a two-dimensional system. Integral between 0 and plus infinity of dx m over beta 1 over e to the x minus 1. Why? Because you see that if I set x equal to p squared, what I have is that dx is equal to p divided by m times beta dp. And pdp is exactly this combination. So that's why I get dx as a result. So this is equal to a over 2 pi times m over beta times the integral between 0 and plus infinity dx of 1 over e to the x minus 1. All right. So now, what is this? Does this equation have a solution? So is there a temperature for which, what is the temperature for which the chemical potential is equal to 0? Well, so so beta is equal to 1 over kBt, right? So this is n equal to a over 2 pi kBt times m times this integral. And therefore, what I get is that my Tc in this case is n divided by all of this stuff, right? A over 2 pi times kbm times integral 0 plus infinity dx 1 over e to the x minus 1. Right?
Yeah.
Is Tc, so what is the value of Tc in practice? Is it finite? Is Tc finite? So is Tc finite?
No, I think.
No. Why?
Yeah.
So is it equal to what?
I mean, because of the integral,
Yes, because of the integral, which is
which is the ln ex minus 1 minus x. Yeah.
so is this integral finite or not? Is it convergent?
Oh, no, it's diverge. It
The
diverges.
integral is divergent, and therefore Tc is equal to 0 always. Okay?
Yes.
So Tc, in this case, you see that Tc is always equal to 0. Why? Because the integral is divergent. Integral 0 plus infinity dx 1 over e to the x minus 1, of course, is convergent for large x, but it's not convergent for small x in the infrared, because if you expand close to x equals 0, the integrand, it is equal to 1 over 1 plus x minus 1. So it's essentially going like 1 over x, and the integral of 1 over x is not convergent as a logarithmic divergence. Okay? So all of this exercise, just to tell you that if you consider Bose-Einstein condensation in 2 dimensions, in principle, you should not expect to have anything like a finite Bose-Einstein condensation temperature in 2 dimensions. Now, next time, now it's, well, I don't think I have enough time to do the next calculation, but so I leave it to you as an exercise to see what happens in 1 dimension, B, C in 1D. Is there or isn't there Bose-Einstein condensation in 1 dimension? Well, so what you have to do in practice always in order to answer this kind of question is try to solve this equation. Right? Try to find T, C, for which this equation is satisfied. And if you can find a solution, then there is a Bose-Einstein condensation temperature. If you cannot, or if the only solution is T equals 0, then there isn't a transition. Now, you see that when you have an equation of this type, what determines whether you will or you won't find a solution is this function g of epsilon. So in other words, in order to answer the question, is there or isn't there Bose-Einstein condensation in 1 dimension, what you should do is compute the density of states, g of epsilon, and then insert it in here and see whether what you get is convergent or not. Okay? So do me a favor if you have, well, the next lecture is tomorrow at 11, but if you would have time, try to do this exercise. What you should get, you can easily guess. There isn't a Bose-Einstein condensation transition in 1 dimension. Yes.
So I have a question about the previous one. I mean, in the previous several pages before, you said nx smaller than n.
For temperature smaller than Tc.
Yeah, and then you get the mu greater than 0, which is meaningless physically.
Yes.
And then somehow afterwards you can divine that for temperature smaller than Tc, then Nx will occupy the excited states, and the difference between N and Nx will occupy the macroscopic ground state. Why is that so?
Why?
Why is that so? I mean,
because it cannot be otherwise, right?
I
mean,
you said like
mu has to be equal to mu has to. So for temperature smaller than Tc, you cannot satisfy this equation. You cannot satisfy this equation. This one with a negative or 0 mu. So this equation is not satisfied for T smaller than Tc. So what does it mean that this equation is not satisfied? It means that the number of particles that are sitting in this integral are not enough to, I mean, the things that you're putting in this integral are not enough to account for all the particles in the system. But you're not losing particles. These particles are put somewhere. Where? Well, then you remember that this integral comes from a sum. And in this sum, in principle, you should estimate the discrete sum. Now, if in a discrete, when you pass from a sum to an integral, you forget about one of the states. It doesn't matter because it has measure 0. But since here you're lacking space to put particles, then you have to put them somewhere. The most natural choice is to put them in the ground state, because that's the state with highest probability to be occupied. Okay?
Okay.
Are there other questions? Okay, so if not,
about
yes.
About the so tomorrow lecture is 11.
11. Yeah, she made a mistake in sending you the mail, but it's at 11.
I see. So, and also about I think you promised to send us the
I
previous
will.
year's exam. And,
I will send you the exams. Don't worry.
And also, I have questions about the tutorial. So, we don't have tutorial, or?
Well, I don't know how to organize a tutorial. I mean, how can I organize a tutorial?
I mean, so we
to do a
just
tutorial, we have to be physically present. I mean, a tutorial online, I don't know how to organize it.
Oh, well.
So I told you last time, I mean, I can give you some exercises. I can give you books about exercises. I already gave you some, but I don't know how to organize. In order to organize a tutorial, it has to be interactive. I cannot just talk myself and solve problems on the blackboard, which is practically what I've been doing all the time. So you see what I mean?
Yes, yes.
So, I mean, tutorials online are essentially impossible to organize, at least in my view. I don't know. Are you doing tutorials with other courses?
Yeah, for example, in quantum mechanics, the tutors go to the blackboard in room D and write something, and then we just ask questions.
Oh. Well, so well, let me see with Kiselev if I can do something quickly. I mean, myself, I cannot go to room D. Well, let's see. Maybe we spend a couple of lectures doing something like this online. So I give you some exercises. You try to solve them, but then I don't see what you're doing. Then you ask me questions. I don't know. Let's try to do that. Okay.
Okay.
Okay. All right, guys. Okay, so I'll see you tomorrow then. Bye-bye.
Bye.